In this episode, we take a problem that frustrates a lot of learners when they first see how real projects work. Security is often described as important, but it is treated as something separate from the way teams actually build and deliver systems. That separation creates a predictable cycle where security shows up late, finds issues that are expensive to fix, and then gets blamed for slowing things down. A healthier approach is to treat security tasks as normal engineering tasks that can fit into any development methodology, whether a team plans everything up front, iterates in short cycles, or delivers continuously. The key is not to memorize a single perfect process, because organizations work differently, but to understand what security activities must happen and how to place them so they support delivery rather than collide with it. When security is integrated well, it becomes less dramatic, less adversarial, and far more effective because it shapes decisions early and produces evidence steadily. By the end of this session, you should be able to describe how security tasks can be woven into development work without turning the project into a compliance theater or a last-minute crisis. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A useful starting point is to clarify what we mean by a development methodology, because the term can sound like a specific named framework when it is really a pattern of how work moves from idea to working system. Some methodologies emphasize upfront planning and formal handoffs, while others emphasize small increments, frequent feedback, and rapid change. These differences affect timing, but they do not change what security engineering needs in order to succeed, such as clear requirements, strong architecture decisions, careful control of change, and evidence that controls work. If a team ships in short iterations, security tasks must be small, repeatable, and frequent, rather than large one-time reviews. If a team does long phases, security tasks must be placed at the phase transitions so they influence design and integration before the system hardens into something costly to change. Beginners sometimes assume that security integration means forcing everyone to adopt one specific development style, but security engineering can adapt to how teams work as long as the essential activities are not skipped. The exam often tests this adaptability by describing different delivery environments and asking for approaches that preserve security intent without breaking the delivery rhythm. The first security activity that must integrate into any methodology is security requirements work, because requirements define what the system must do and what must be true for it to be acceptable. Requirements integration does not mean dumping a huge list of controls on a team and calling it done, because that creates confusion and resistance. Instead, it means translating security needs into clear, testable statements that align with system goals, such as who can access what must be logged, how sensitive data must be handled, and what evidence must exist for assurance. In a fast-moving environment, requirements may start as high-level constraints and become more detailed as the design evolves, but they still need ownership and traceability. In a more formal environment, requirements may be documented and approved early, but they still need review as assumptions change. A common beginner misunderstanding is that requirements are only functional, like features, while security requirements are somehow optional. Yet security requirements often act as constraints that shape architecture and reduce rework. When requirements are integrated, later security tasks become smoother because the team knows what they are aiming to satisfy. Once requirements exist, the next essential security activity is design and architecture engagement, because security is largely determined by structure, boundaries, and trust assumptions. Integrating security into design means that security engineers participate when interfaces are defined, when data flows are chosen, and when responsibilities are assigned to components. This is where you decide where trust boundaries exist, how identities will be verified, how authorization will be enforced, and how monitoring signals will be produced. In an iterative methodology, design decisions might happen repeatedly in smaller chunks, so security participation must also happen repeatedly, focusing on the most impactful boundaries and changes each time. In a phased methodology, design decisions might be concentrated earlier, So security input must be present during those earlier decisions rather than arriving after the design is considered finished. A predictable failure mode is treating design as purely technical and then trying to patch security with add-on controls later, which often leads to complexity and weak assurance. Another predictable failure mode is skipping threat thinking during design, which leaves the team blind to how attackers might exploit interfaces and trust assumptions. Integrating design security work is less about writing long documents and more about making sure key decisions are made with security in mind and recorded clearly enough to preserve intent. A third security activity that fits any methodology is threat-informed analysis, which is often misunderstood as an advanced exercise reserved for specialists. In simple terms, this activity is about asking what could go wrong, how it could happen, and what would be most damaging, using the system's design and context as your guide. The purpose is not to predict every possible attack, but to identify the most plausible and most harmful paths so the design can be strengthened early. In iterative delivery, this can be done in small slices, focusing on the piece of the system being built next and updating the analysis as the system evolves. In more structured delivery, it can be done as a formal step, but it should still be revisited when major changes occur. Beginners sometimes think threat thinking means chasing scary stories, yet the real value is that it forces clarity about trust boundaries, inputs, identities, and dependencies. It also helps prioritize security tasks, because you can focus on controls that block the most plausible and damaging failures rather than spreading effort evenly. When exam scenarios mention complex integrations, new exposure, or unclear boundaries, a threat-informed approach often becomes the right mental move because it connects design choices to risk paths. Security tasks also need to integrate into implementation work, but that does not require turning developers into security specialists or forcing step-by-step security rituals that slow every action. Integration at implementation means establishing consistent secure patterns for common tasks, such as handling inputs safely, enforcing authorization consistently, managing secrets responsibly, and failing safely when errors occur. It also means ensuring that security controls specified in design are actually implemented as intended, rather than being approximated or postponed. In an iterative methodology, this often looks like embedding security checks into definition of done expectations, so a feature is not complete unless its security requirements are met and its behavior is verifiable. In a phased methodology, it can involve implementation standards and peer review practices that focus on correctness and consistency, not just functionality. A beginner misunderstanding is that secure implementation is mostly about adding encryption everywhere, but secure implementation is often about preventing unintended behaviors, limiting privileges, and ensuring consistent enforcement. If security implementation work is integrated, it reduces late-stage surprises because the system's security posture grows alongside its features. It also supports assurance because you can connect requirements and design decisions to real behavior in code and configuration. Verification is the next place integration matters, because a system that looks secure in design can still fail if security behaviors are not tested and validated. Verification in security engineering means checking that controls work as specified, that boundaries enforce the right rules, and that failure conditions do not create unsafe outcomes. In iterative methodologies, verification should be continuous and incremental, meaning each change is checked for security impact and regressions, rather than waiting for a giant test phase at the end. In more traditional approaches, verification may be concentrated later, but security verification still needs planning early so the right tests and evidence collection exist when needed. Beginners sometimes treat testing as one event, yet security verification often involves multiple types of evidence, including functional checks of access control, validation of logging and audit trails, and reviews that confirm configuration baselines. Another misunderstanding is assuming that passing tests once proves security forever, when in reality verification must keep pace with change or confidence decays. Integrating verification tasks helps delivery because it finds issues earlier when they are cheaper to fix, and because it reduces the risk of late-stage failures that delay release. On the exam, answers that emphasize steady evidence and early detection of issues often reflect a mature understanding of integration. A closely connected activity is validation, which asks whether the system meets real needs and behaves securely in its intended environment, not just whether it matches written requirements. Validation matters because requirements can be incomplete, assumptions can be wrong, and real-world usage can expose behaviors that were not anticipated. Integrating validation means creating feedback loops with stakeholders and operations so that security expectations remain aligned with how the system is actually used. In iterative delivery, validation can happen through frequent review of system behavior, operational constraints, and user workflows, ensuring security controls are effective without being bypassed. In phased delivery, validation can appear as readiness reviews and acceptance checks that confirm the system is fit for real operation, including security readiness. Beginners often assume that if a system is technically secure, users will follow the intended path, but security that ignores usability and workflow reality is often bypassed, which creates risk regardless of design quality. Validation also includes confirming that monitoring and response capabilities work in practice, because a system's security is partly defined by how quickly it can detect and respond to abnormal behavior. Integrating validation prevents the failure mode, where a system passes a paper review but fails when it meets real people and real operational pressure. Configuration management is another security activity that must integrate into any methodology, because uncontrolled change is one of the fastest ways to destroy security posture. Configuration management is about defining baselines, controlling changes, and maintaining traceability so you can always answer what is deployed, what changed, and why it changed. In iterative methodologies, change happens frequently, so configuration management must be streamlined and consistent rather than heavy and slow, otherwise teams will bypass it. In more formal methodologies, configuration management may be stricter and more centralized, but it still needs to support timely changes, especially for security fixes. Beginners often think configuration is an operations concern and code is a development concern, but modern systems blur those lines, and security posture depends on both code and configuration staying aligned with intent. Without disciplined configuration management, monitoring alerts become harder to interpret, audits become painful, and incident response becomes slower because nobody is sure what state the system is in. Integrating configuration management into delivery means treating baseline updates, approvals, and documentation as part of normal work rather than as a separate administrative burden. Exam scenarios that mention drift, inconsistent environments, or repeated reintroduction of issues often point toward missing configuration discipline. A related integration point is vulnerability management, which is sometimes treated as a purely reactive activity, but is actually a continuous part of secure delivery. Vulnerability management includes identifying weaknesses, prioritizing them based on risk, applying fixes, and confirming that fixes actually reduce exposure without creating new issues. In iterative methodologies, this can be integrated as a regular refinement loop where known issues are tracked, risk is assessed, and fixes are planned into upcoming work based on impact. In phased methodologies, vulnerability management may appear as formal assessment and remediation cycles, but it still must connect to the development and change process so fixes are not stalled. Beginners sometimes assume that security fixes are always urgent and must override everything. But mature security engineering prioritizes based on context, exposure, and mission impact, while still maintaining accountability for decisions. Another misunderstanding is assuming that fixing one weakness ends the story, when in reality you need to confirm the fix, update baselines, and watch for regressions. Integrating vulnerability management supports delivery because it prevents a backlog of unresolved issues from becoming a release blocker later. It also supports assurance because it creates a traceable record of how risk is managed over time. Logging and monitoring integration is another essential activity, because systems that cannot be observed cannot be defended with confidence. Integrating monitoring means designing logs and signals intentionally so that security-relevant events can be detected and investigated without guesswork. This includes thinking about what events should be recorded, how identity and context are captured, and how logs support accountability for sensitive actions. In iterative methodologies, observability must be added as features are built, because waiting until the end often leads to missing context and incomplete coverage. In more structured approaches, monitoring requirements can be specified early and verified during integration testing, but they still require careful implementation choices in each component. Beginners sometimes treat logging as a performance nuisance or an afterthought, yet in security engineering, logging is part of assurance evidence and part of operational safety. Poor logging creates predictable failure modes, such as not knowing whether an incident occurred, not being able to trace an action to an identity, or not being able to determine what data was accessed. Integrating monitoring into delivery also helps avoid the trap of building controls you cannot verify, because observation is a key part of proving that controls work. Exam questions that involve incident response, uncertain security posture, or accountability often reward answers that include thoughtful monitoring integration. Security review and approval activities also need integration, but the goal is to make them predictable and lightweight, not to create random interruptions. Reviews are most helpful when they happen at the points where decisions are still flexible, such as during requirements formation, before major architecture commitments, and before operational release. In iterative methodologies, reviews can be smaller and more frequent, focusing on the changes introduced in each iteration and ensuring they align with security requirements and do not introduce new trust problems. In phased methodologies, reviews can align with phase transitions, ensuring that each stage produces the expected evidence and that risks are addressed before moving forward. Beginners sometimes fear reviews because they associate them with rejection, but a well-run review process is about clarifying risk, confirming evidence, and preventing surprises. Approvals also matter because they establish accountability, ensuring that decisions about risk acceptance, exceptions, and operational readiness are made by the right authorities. If approvals are integrated as planned gates with clear criteria, they support delivery by reducing rework and by keeping stakeholders aligned. In exam scenarios, where governance and delivery collide, the best answers often involve improving the timing and clarity of review gates rather than eliminating oversight. An important part of integration is tailoring security tasks to fit the methodology without losing the essentials, because different environments demand different rhythms. In a highly iterative environment, security tasks should be small, repeatable, and embedded into normal work habits, so security becomes a steady stream of quality rather than a single flood at the end. In an environment with formal phases, security tasks should be aligned to the phase boundaries and supported by strong traceability so evidence accumulates logically. In both cases, the essential security activities remain the same in spirit: define clear requirements, shape secure design, evaluate threats, implement consistent controls, verify and validate behavior, control change, manage vulnerabilities, and observe the system in operation. Beginners sometimes think tailoring means lowering standards, but in security engineering, tailoring means adjusting how you achieve a standard so it fits reality and remains sustainable. A security process that looks perfect on paper but is bypassed in practice produces worse outcomes than a lighter process that is consistently followed and produces reliable evidence. The exam tends to reward candidates who can preserve essentials while adapting form to context, because that demonstrates real engineering judgment. When you can explain how to integrate tasks without breaking the team's flow, you show you understand both security and delivery. Another beginner-friendly way to understand integration is to see security tasks as supporting the same goals that development methodologies claim to support, such as predictability, quality, and learning. Predictability improves when requirements are clear, when change is controlled, and when risk decisions are documented, because teams are not surprised by hidden constraints. Quality improves when security controls are built and tested alongside features, because defects are found early and fixed cheaply. Learning improves when monitoring provides feedback and when incidents and near misses are analyzed and turned into better requirements and better design choices. In other words, integrated security is not a separate goal competing with delivery. It strengthens the same outcomes that good delivery aims for. Beginners sometimes assume that security always slows things down, but late security issues slow things down far more than steady integration does. Security tasks kill delivery only when they are unpredictable, inconsistent, or divorced from how work is actually done. When security tasks are treated as normal engineering work with clear criteria and repeatable practices, delivery becomes smoother because the project avoids chaos and crisis. Exam scenarios that describe recurring friction often point toward integration problems rather than security itself being incompatible with delivery. As we close, the big idea is that integrating security tasks into any development methodology is less about adopting a specific label and more about ensuring that essential security activities happen at the right times, at the right scale, and with the right evidence. Requirements work must include security constraints so design does not drift, and design engagement must identify trust boundaries so controls are structural rather than cosmetic. Threat-informed thinking must guide priorities so effort reduces meaningful risk, while implementation practices must enforce consistent secure behavior rather than relying on last-minute fixes. Verification and validation must keep pace with change so assurance stays real, and configuration management must preserve intent so the system does not quietly drift into insecurity. Vulnerability management and monitoring must be continuous so the system remains defensible after release, and review and approval gates must be predictable so accountability supports flow rather than interrupting it. When you can explain how these activities adapt to iterative, phased, or hybrid delivery without losing their purpose, you demonstrate the kind of mature reasoning ISSEP expects. If you carry that mindset forward, you will be able to read almost any scenario and describe a security integration approach that is realistic, evidence-driven, and aligned with delivery outcomes.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.